All right, hello everybody. Welcome to the next Physics 216 video. We're actually coming up to, really the last topics that we're going to talk about in this course. And that last topic is the motion of rockets. We'll consider a few different situations, cases where there are no forces acting on our rocket, cases where our rocket is traveling through a gravitational field, cases where the rocket is traveling through some kind of medium that exerts a drag force on it, like the atmosphere of the Earth or something like that. And then possibly situations where we both have gravitational field and a drag force acting on our rocket. More generally, the type of analysis that we're going to do can be applied to any kind of body which has a mass that varies as it moves. So it's the motion of bodies with variable mass. Okay, so as a starting point, let's consider the following situation. Let's consider an object with mass m of t. So I'm going to write the mass as a function of time because we're going to allow the mass of this object to change. And so we could have a scenario where this object moves through some kind of medium and it absorbs mass as it moves through that medium. So our object absorbs mass, let's say at a constant rate as it moves. Okay, so for example, an object moves through a medium in which there are small particles, are suspended. And every time our object collides with one of these small particles, it's a perfectly inelastic collision. That is, the particles stick to the larger mass. So the particles that collide with the object stick to it. So one thing, maybe you could imagine that you take a ball and you throw it through the air and it's raining outside, and maybe this ball is made of some material that absorbs the little raindrops when it hits the ball. Okay, so the picture is the following. We're going to have some object, and this is the object that has variable mass. And initially, it's moving with some velocity v of t. Then what we do is let's just say it's moving with some speed v of t. And then what we're going to do is we're going to have a small little particle of mass, delta m, and it's moving with some speed u of t. And if we make v greater than u, then eventually our big mass will collide with delta m. And after that collision, what we assume is that we've got our object that has some mass at some later time after the collision. So let's say the collision occurs at a time delta t after our initial time t. Okay, so this is the mass at some later time, and what it's going to be equal to is the initial mass of our object plus the amount of absorbed mass. And if it collided with a single particle, that absorbed mass is delta m. And so we could try to indicate like our single particle here has been splattered onto the edge of our big mass. And at this later time, we're going to have some speed at time t plus delta t, which is going to be equal to the speed that our mass initially had plus some delta v. Now, if we drew it in the way that we have shown in the picture on the left side of the screen, then we might anticipate that the delta v would be negative, like our big mass would end up slowing down. But we could also have a scenario where maybe particles come from behind and run into our big mass, and maybe they give a positive delta v. Okay, so what we need to do is we need to conserve momentum. So momentum conservation. So the change in momentum of our system is going to be equal to the initial momentum. Well, in fact, the change in momentum will be the final momentum minus the initial momentum. So what's the final momentum? Well, it is the final mass of our object, which is m plus the absorbed mass, delta m. And we multiply that by the final velocity. And if we're calculating the change in momentum, what we need to do is we need to subtract off the initial momentum. And initially we have two objects. And so our first object is, say, our large particle, which has mass m and velocity v. And then there's also the momentum of the small mass, delta m. And so it has velocity u and mass delta m, like so. And so here is the final system momentum, and here is the initial system momentum, and we take the difference between the two. Okay, so I'm going to define a quantity big V. And so we're going to have to be a little bit careful here, because I'm going to use a little v to indicate the speed of our large particle. And I'm going to use big V to indicate our relative velocity. Big V is the velocity of our particle delta m relative to big M. So the question then is, suppose that you were riding along on top of this big mass, and so you're moving at some constant speed v, and you look out, maybe there's a window on this big mass, and you look out the window and you look at this particle delta m. And so the question is, what would be the speed that you would observe for delta m? So an observer on the large mass m of t looks at delta m, and the speed that they would measure would be equal to delta m's speed relative to a fixed observer, u of t, minus the speed that the observer is moving at, v. So this relative velocity is given by u minus little v. Or what we could do is we could solve for u, and we could say that that is going to be big V plus little v. And what we'll do is we'll make this substitution for u in here. Okay, so after making that substitution, let's see what we have for the change in momentum of our system. Okay, so we have little m times v plus little m times delta v plus delta m times v plus delta m times delta v. Okay, and then we have, so that's all the final momentum contributions. And then we have minus mv plus, for u, we're going to write v plus little v, big V plus little v times delta m. Okay, and so we get mv plus m delta v plus delta m v plus delta m delta v. And what do we have? We have minus mv, and then we have minus delta m big V, and then we have minus delta m little v. Okay, so we can probably find some cancellations. We have mv and we have minus mv. And what else do we have? We have delta mv and minus delta mv. Okay, so the remaining terms then are m delta v plus delta m delta v, and then we have minus big V delta m. Okay, there's a common factor of delta v, so we could write this as m plus delta m times delta v minus v delta m. Okay, so if we go back to our picture, then what we assumed is that the mass delta m was absorbed in a time delta t. And so let's say on average we get an absorption of mass delta m in time delta t. And that's constant. We assumed from the beginning that we were going to absorb mass at a constant rate. So we're going to assume that that's constant. So if mass delta m is absorbed in a time delta t, then what we can do is we can take our expression and just divide all terms by delta t. On the left-hand side, we have the change in the system momentum, and so we would get delta p of our system divided by delta t is equal to m plus delta m, and then we take delta v and divide by delta t. And then we have minus v, this relative velocity of delta m, and then we have delta m divided by delta t. Okay, so, I mean, that obviously looks like some derivatives, right? So we're going to take the limit that delta t goes to 0, and so we'll say that delta v over delta t, we're going to write that as the time derivative of v, the velocity of our big mass, which in the end maybe we'll call that big mass our rocket. And this delta m over delta t is the rate of mass change, and so that's m dot. Just thinking ahead, if we're thinking about our rocket's going to be burning fuel, and so we might anticipate that our delta m will be negative, so that means that our m dot will be negative. Okay, the other thing that we have is when we take the limit that delta t goes to 0, we've got a m plus delta m. And so if we take a really small time interval, then the delta m compared to the total mass of our object is going to vanish. And so we're going to say that delta m goes to 0 in the 0 time limit. Okay. The other thing that we'll notice is that we have the system momentum, the change in the system momentum divided by the time interval. And if we take the limit that delta t goes to 0, this becomes the derivative of the system momentum with respect to time. But the time derivative of momentum is force, right? So think of what momentum is. It's mass times velocity. And then we take a derivative, then we'll get something like mass times acceleration, which is force. And so this is just equal to the net external force on our system. Remember, we did this argument in the last video that the internal forces don't matter because they end up canceling out. So this is the net external force. Net external force. Okay, so then what we've got for our expression then is that on the left-hand side we have the external force is equal to m v dot minus big V m dot. And so this is an expression that we will probably come back to a few times when we consider different cases, different scenarios. Okay, so the first scenario is the case of a rocket burning fuel. And so we already discussed that in this case, we will have an m dot that is negative because the rocket will be losing mass as it burns fuel. So rocket loses mass as it ejects burnt fuel. Okay, just some jargon. If you're reading about this in a textbook or online or something like that, you might find the term big V, the relative velocity of the delta m mass times m dot. This term is called the thrust of the rocket. So you could see that, you can see that this term, the thrust, is equal to F external with some other term mv dot in there, mass times acceleration. And so the units of thrust are newtons. Okay, so for a rocket in deep space, what we would do is we would say F external is equal to 0. So we assume that, in deep space, space is is a very good vacuum, and so there's no drag force from an atmosphere. So no drag forces due to some kind of atmosphere. And let's say there's no gravitational force due to a nearby mass. So we're not near the sun, or we're not near some planet or some black hole or something like that. Okay, so then if we go back to our expression over here, we're going to set F external equal to 0. and we're just going to have an m v dot minus v m dot. So therefore, what we have is 0 is equal to m v dot minus v m dot. And so I'm trying to be consistent in drawing my two different velocities, one capital uppercase and one lowercase. Okay, so what we have is m dv dt, that's v dot, is equal to, so we'll take the minus v m dot to the other side, and so that's d big V dt. Oh, sorry, that's not right. The derivative is on m, so we have v dm dt. Okay, and so we have two terms, each have a derivative with respect to time, so we can cancel that dt. And therefore, if we divide by m and integrate, what do we get? We get the integral of dv is equal to the integral of v dm over m. Okay, so let's think about the case where our rocket burns fuel at a constant rate. So we're going to assume that the rocket, I guess what I want to assume is that the rocket is going to eject fuel at a constant relative speed. So this capital V we're going to assume is constant. So even as the rocket maybe moves faster or its mass decreases as we burn more and more fuel, we're going to assume that we can always eject the fuel at the same relative speed out the back of the rocket. So we assume that the rocket ejects fuel at a constant relative speed v. Okay, so that simplifies things quite a bit, because if the v is a constant, we can take it outside the integral, and we would have the integral of dv is equal to v times dm over m. Okay, so let's think about our vectors a little bit. What we're going to have is we're going to have a rocket. Let's say it's moving towards the top of the screen, and so it has a velocity v towards the top of the screen. And then what it's doing is it's ejecting particles, that is the burnt fuel, and those particles have some velocity, and what they'll actually do is they'll actually be, let me change the color here, those particles will have a speed u that will follow behind the rocket. So think of it this way, you are on a rocket and you're going to take a ball and you're going to throw it out the back of the rocket. But let's imagine your rocket's moving really, really fast, like 1,000 kilometers a second or something like that. And then what you're going to do is you're going to throw the ball out the back as hard as you can. And so maybe you could throw the ball at 100 meters per second. Well, that's the 100 meters per second is the speed relative to you, and you're moving very fast in the opposite direction. And so the actual velocity of the ball, as observed by someone in a fixed coordinate system, say observed on the moon or something like that, they'll see you moving very, very fast in one direction, and then they'll see the ball chasing you just at a slower speed. And so what we have is that the ejected fuel has a velocity u in the same direction as v, but the magnitude of u is less than the magnitude of v. So they're moving in the same direction, just at different speeds. Okay, so then if we recall our definition of the relative velocity, that was equal to u minus v. And so if u and v are in the same direction, but v has a larger magnitude, what we get is that v is in the opposite direction of v. So what we're going to do is we're going to treat our vectors as, well, and in fact, if we're throwing mass out the back of our rocket, we're going to expect the velocity of our rocket to increase. And so that means that big V is also in the opposite direction of the change in the velocity of the rocket. So what we'll do is we'll say, let's say that we can use, just for this one-dimensional problem, we'll use the positive sign to indicate the direction of our vectors. So dv is going to go to plus dv if we take the positive towards the top of the screen, and big V is going to go to minus v, because that is a vector that is in the direction opposite of v and dv and of u for that matter. So v, which is equal to u minus v, is in this direction towards the bottom of the screen. Okay, so if we do all those things, then we could say that we have the integral of dv is equal to now minus big V times the integral of dm over m. So let's put in some integration limits. So we'll say initially the rocket speed is v0 when its mass is m0, and then at a later time the speed is v and the mass is m. Okay, so then what we would have is the integral of v0 to v dv is equal to minus capital V, the integral from m0 to m of dm over m. Okay, this is v minus v0, and this integral is going to be the ln of, let's see, m minus the ln of m0, which is equal to the ln of m over m0. Okay, so what we have therefore is that v minus v0 is equal to minus v ln of m over m0, or v is equal to v0 plus, we could absorb the minus sign into the ln, and what that does is it flips the argument of the ln, m0 over m. And so this is the rocket equation for the case of f external is equal to 0 and for the relative velocity of our fuel is equal to a constant. So if you have some initial mass, m0, of your rocket, which includes the body of the rocket plus the fuel that it's carrying, and then you have some final mass, suppose you burn all the fuel, and so the final mass is just the mass of the rocket itself, then you could calculate the change in velocity of the rocket from as a result of burning all that fuel if you know the speed with which the fuel is ejected. And so let's do that. So let's do an example. Let's suppose that if the ejected fuel has a relative velocity of 3 kilometers per second, then we could ask how much fuel is required to take a rocket in deep space from rest to 8 kilometers per second. Okay, well, let's just write down our rocket equation. It was final speed is equal to the initial speed plus the relative speed of the fuel, ln of m0 over m. Okay, well, we said our rocket was going to start at rest, so v0 is equal to 0. So what we could do is we could divide by big V, take the exponential, and so we would have the exponential of little v divided by big V is m0 over m. And so that would mean, therefore, that m0 over m would be equal to E. We wanted a final speed of 8 kilometers per second with a relative velocity of fuel at 3 kilometers per second. And so if you put that into your calculator, you get 14.4. And so that means the initial mass has to be 14.4 times the final mass. And so the change in mass of the rocket is equal to its initial mass minus the final mass. And so that's just going to be 14.4 m minus m, which is 13.4 m. And so this must be the change in mass is how much fuel that we've burnt. And so this is the mass delta m of the fuel. And so we could express this as, say, a ratio. The mass of the fuel delta m divided by the final mass. And so if we're assuming we burnt all the fuel, this is now just the mass of the rocket. So mass of rocket after all fuel is burnt. And so that would just be equal to 13.4. Oh, sorry. I wanted to do something else. Sorry. I want this to be... Sorry about this. Let me start this over. I want to take this ratio, but I want to take the mass of the fuel divided by the total mass of... This is total initial mass of the rocket body plus all the fuel. Okay, and so that delta m is 13.4 times m, and m0 is 14.4 times m, and so that ratio comes out to be about 0.93. And so what that tells us is that to achieve what we wanted, to go from rest to 8 kilometers per second, when we eject fuel with a relative velocity of 3 kilometers per second, that means that our rocket initially has to be 90% fuel. So therefore, 93% of the rocket mass is burnt fuel in this case. And so that's obviously expensive, right? So if you wanted to actually do that in practice, you're going to spend a lot of money filling up your rocket with a lot of fuel. We won't discuss the details, but one way to do better is to have multistage rockets where you have part of your body filled with fuel, and then you burn that, and once you've burnt that fuel, then you eject the container that was holding that fuel, and so you reduce your mass a little bit more, and then you start burning another stage of fuel, and once you've burnt all that, then you eject the container holding the fuel, and so you're left with only your payload, and so you can gain efficiency by kind of designing your rocket in a clever way, and it's the multi-stage rockets that allow you to do that. Okay, I want to do one other thing in this video, and I want to consider rockets in a gravitational field. Gravitational field. In this last example, we had a rocket in deep space, and we said F external was going to be 0. So now we're going to have some non-zero F external. Okay, so what if our rocket was launched from Earth, where F external has a magnitude equal to mg? What we'll do is, for simplicity, we're going to assume that this force doesn't change as the rocket gains altitude. For simplicity, we will assume that G remains approximately constant. Well, we're going to assume that it just remains constant as the rocket moves away from Earth. Of course, this isn't true. If the rocket gets to an altitude that's a substantial fraction of the radius of the Earth, then there'll be a noticeable decrease in the gravitational force due to the Earth. But for the sake of working on a problem that we can solve analytically, we'll consider this F external constant case. So this might be approximately valid if you're trying to launch an object just into low Earth orbit, or maybe what we can do is we can say, well, this analysis is valid for just the early stages of the rocket's motion, where it's launched from the Earth's surface and, initially remains relatively close to the Earth's surface. Okay, there's another thing that we're not going to take into account in this problem, and that is the drag due to the Earth's atmosphere. So that's something that I think we'll start to think about in the next and the final Physics 216 video. Okay, so we're going to go back to our expression of F external is equal to, this time we'll set it equal to mg, and if you look back, one of our expressions looked like this. In fact, we could probably find it pretty easily. It is this thing right here. So we're starting with this expression. The only thing we've done is we've set the external force equal to mg. Okay, so let's draw a picture of this scenario where this is going to be Earth, and here's our rocket, like this. And so the relative velocity of the ejected fuel is in the opposite direction of the rocket's velocity. So we have little v and big V. And now we have a gravitational field that points downwards. And what we'll do is we'll take vertical upwards to the top of the screen as the positive direction. So what that means is that we're going to have m v dot is going to be m dv dt. And we're going to take that as positive because if we're ejecting fuel, we expect our dv to be positive. It's going to increase in speed. Okay, and then we have minus v, but the vector v points down, and so minus that negative direction ends up being a plus v, and then we have a dm dt is equal to mg, but g points downwards, and so what we get is a minus mg. Okay, what we did last time is we multiplied by dt, and so let's do that again. Last time when we did that multiplication, the dt just vanished. We're not going to have as simple a case this time because we have a non-zero term on our right-hand side, and so we have to multiply by dt. Okay, so then let's divide by m. And so what do we get? dv plus v dm over m is equal to minus g dt. Okay, so the last thing I'm going to do is I'm going to divide by big V, the relative velocity of our ejected fuel. And so we would get dv over big V. And then we'll put minus. So I'm going to take the dm over m to the other side. And then we'll have g. Remember, we divided by big V, so we still have that, and dt. And so this is a differential equation for a rocket in a gravitational field G, where we've assumed G to be constant. Okay, so we are going to now integrate, and we're going to assume that V and G are constants. And so we get 1 over big V, the integral. And so let's suppose that our rocket is launching from the surface of the Earth, starting from rest, and then it's going to reach some final velocity. And so we're going to have some initial mass of our rocket, which is going to include the rocket and the fuel. And we're going to have some final mass of our rocket after we burn some of that fuel. And then we have minus g over big V. And we're going to go from liftoff at t equals 0 to some final time tb, which I'm going to call the burnout time. So it's the time after which we burnt all our fuel. So TB is the burnout time. So a time after which we've used up all the fuel. Okay, so we're going to say that the initial mass at launch is equal to the mass of our rocket. So mass of rocket, which is essentially going to be our fuel container. Okay, and then what else are we going to have? M, and so we already used MF for our final mass, so I'm going to say M fuel. And so that's obviously the mass of the fuel. And then I'm going to separate out from the mass of the rocket the mass of the payload. So maybe what we're trying to do is to deliver a satellite into low Earth orbit or something like that. And so this is the mass of the payload. And so this is really the object, such as a satellite or something. This is the object to be put into orbit. Okay, so the final mass is just everything after we've burnt our fuel. So it's the mass of our rocket plus the mass of our payload. Okay, so when we do the integration, what we're going to get is VF over V is equal to, so let's say this is a large V. And then we're going to get minus the ln of M. And so we're going to go from initial mass to some final mass. And then we're going to get minus G over V. And the integral of dt is just going to end up being the burnout time. Okay, so we get VF over V is equal to, let's see, minus the ln of MF over M0. So the final mass was rocket plus payload, and the initial mass was rocket plus payload plus fuel. And then we have minus GV over the times burnout time. All right, so let's see, what we could do is we could write this as VF plus G times T burnout over the relative velocity of the fuel is equal to, we have minus ln, so I could write that as the ln of the inverse of what we had. So the denominator becomes the numerator, and the numerator becomes the denominator. And let's see, we could break this up now. So we could break this up into mass of the rocket plus mass of the payload divided by mass of rocket plus the mass of the payload, which is 1, plus the mass of the fuel divided by the mass of the rocket plus the mass of the payload. And then exponentiating both sides, we could get that the mass of the fuel is divided by mass of the rocket plus the mass of the payload is equal to the exponential of, what do we have, G times the burnout time plus the final speed of our rocket divided by the exhaust relative velocity. And then we would have a 1, so we're going to subtract 1. So here's a question. Having done this analysis, we can ask, how much fuel is needed to deliver the rocket and payload into low Earth orbit. Okay, so let's suppose that we talk to NASA and they say, well, in order to do this, we have to reach a final velocity of 8 kilometers per second, and we need to use we need to eject fuel at a relative velocity of 3 meters per second. Okay, and the typical burnout time is 10 minutes, or 60 seconds per minute, 600 seconds. And so if those are the parameters of a launch, then you could put those numbers in, and if you do that, you will find that mass of the fuel divided by the mass of the rocket plus the mass of the payload is something like 101. So that means for every kilogram of stuff, and so our stuff in this case are our fuel containers, which is the rocket, and the payload, which is the satellite that we want to put into orbit. So for every kilogram of that kind of stuff that we want to move into low Earth orbit, we require 101 kilograms of fuel. And so again, what people would actually do is to build and design multi-stage rockets. But that's not something that I want to discuss in detail. So if that's something you're interested in, you could try to look up some of the details in a textbook or online. But what we will do in the next video is we will say, okay, can we solve the rocket equation when the external force is some kind of drag due to interactions of the rocket with the atmosphere? And it will turn out that yes, we can do that. And then we'll ask, obviously when we launch a rocket, what you have is both a gravitational force and a drag force. And so what happens when you try to consider both of those things at the same time? Okay, and so that's what we have to look forward to. Thank you very much.